The last section we'll be actually covering in this chapter is on ultraviolet spectroscopy. There are a couple other sections in this chapter which are interesting for you to read, like polymerization of dienes and the chemistry and physics of vision. Be sure to read through those. They're very interesting. Not something that we need to cover in depth in our videos here. Ultraviolet spectroscopy is directly related to what we've been talking about here. Let's get ourselves oriented. Ultraviolet is higher in energy than visible light, right? If we go highest in energy over here, here we've got visible, infrared, and so on. So higher in energy, which means shorter wavelengths, higher frequency. Turns out ultraviolet light is of just the right amount of energy to be absorbed when an electron from the highest occupied molecular orbital is promoted to the lowest unoccupied molecular orbital of a conjugated pi system, such as in butadiene. Okay? It's a form of spectroscopy because some sort of light or radiation is absorbed by the substance. So it's the same sort of idea. Ultraviolet sources shine through the sample. Detector will see what frequencies did not make it through, what wavelengths of light were absorbed. Highly conjugated systems have a smaller gap between the HOMO and LUMO. Let's first make sure we understand that. If I just have ethylene, okay, I'll have just two molecular orbitals, and that's it. Okay, two electrons in the lower of the two orbitals. Okay, if we go up to butadiene, okay, two double bonds conjugated together. Now I'll have four molecular orbitals, but they'll be a little tighter together in energy. Now, four will be occupied like that. If I go up to three conjugated double bonds, 1, 2, 3, 4, 5, 6, 1, 3, 5 hexatriene. The lowest energy one will be a little lower, but still they'll be closer together yet. 2, 3, 4, 5, 6. Something like that. And now I'll have 6 electrons. In each case, here's the highest occupied up to the lowest unoccupied. In ethylene, okay, or really in any isolated double bond like that, there's a fairly large gap between HOMO and LUMO. As we get conjugating, the gap between HOMO and LUMO gets smaller and smaller. Okay? So that means lower energy, right? If I continued conjugating, if I had, 1, 2, 3, 6, if I had 8 or 10 molecular orbitals like that, that gap gets smaller and smaller and smaller. Smaller energy gap, which will require lower energy ultraviolet light. And remember, lower energy is the same as longer wavelength. So the wavelength of ultraviolet radiation that's absorbed gives us an idea of how many double bonds are conjugated together. Okay? If it's at a fairly low wavelength, it's not conjugated at all. Intermediate wavelengths might just have two double bonds conjugated together. Highest wavelengths have multiple sets of double bonds that are conjugated in together. This is what a UV spectrum actually looks like. Notice it's inverted from infrared. Absorbance goes up now, whereas infrared absorptions were valleys, right, were dips in the spectrum. Here, the regions where there's no absorption at all, that's down towards the baseline here. And the point we're looking for is the point of maximum absorbance. Right? It's called lambda max. Right? Lambda is the wavelength, right, down here. So it's not the maximum wavelength, it's the wavelength where absorbance was at a maximum. If any of you did the Beer's Law lab long time ago, back in general chemistry, what you generally did was you investigated multiple different colors and you found the one that had the highest absorbance, right? So, and you ended up using that one to do the rest of your sample. Well, a UV-Vis spectrometer reads all of the wavelengths and gives you this nice chart. So the maximum on there, you can just read off that at 217 nanometers, right, these wavelengths are in nanometers, 217 nanometers is the wavelength where the largest amount of ultraviolet light was absorbed. Okay? That's the value that gets quoted in ultraviolet spectroscopy. So a couple of general rules of thumb. If lambda max is below 200, the compound is usually not conjugated. That's like that ethylene that I showed you. The gap between HOMO and LUMO is just too large, so we need very high energy UV light way down there. A single conjugation might be around 220. Multiple conjugations can get up towards 300. So be careful what I said here. Single conjugation means 2 double bonds. You can't just have one thing, one double bond conjugated. Just clarify that. So here is 2 double bonds that are conjugated. It's a 2-methyl-1,3-butadiene. Okay? So let's predict. I have this box here covering up what the actual ones. So I'll say about 220, just based on those rules there. Here's another one, just 2 double bonds conjugated, about 220. Okay. Here I've got 3 double bonds conjugated, and then I've got 4 double bonds conjugated. I said multiple can approach 300, so I don't know, let's just guess. 250, let's say 290, approximately. Those are supposed to be squiggles. Okay. Here's a butene-one. Okay. It's not just a conjugated alkene, it's a double bond conjugated in with a carbonyl with a C double bond O, but still, that's the same sort of conjugation. I'll guess around 220. Okay. Here I have benzene, and benzene is interesting. We'll see in the next chapter that this is aromatic. This is not just like 3 conjugated double bonds. There's extra stability earned with aromaticity. So I'm going to say, since there's extra stability, really low, 200. And that's sort of weird. It's like they're not conjugated at all, but we'll see. We'll actually hold this thought a little bit, and we'll come back to it when we study benzene in the next chapter, because we'll draw its molecular orbital diagram, and it'll make a little more sense to us then why this is low, like, pretty much like just 1 double bond would be. So I haven't looked at these in a while, I promise. Let's see how close I was. So we've got a double bond here, 220. Yeah, so 1 conjugation like that, 220. This one in the ring, I guess 220. It's actually higher. Going around in that ring when it's locked in that 1 conformation where it can't rotate, that makes it a little more favorable. But that's not something we should be able to really predict. I said 250 for the 3 double bonds. That's not bad. 258. Ooh, it was right on for 290 with the 4 double bonds. All right, it's a pretty good rule of thumb. Multiple conjugations can approach 300. The 2 double bonds in diene-one, right around the normal 2 double bonds conjugated, just like butadiene. Benzene 203. Yep, that's what I would suspect. There's actually a larger gap between HOMO and LUMO in benzene than there is most of any of these, and like I said, we'll discuss that quite a bit later on. So I would like you to know for UV-Vis, I would like you to know 220 for a butadiene. For 2 double bonds conjugated, 220. For more conjugated, it's going to be a higher wavelength. Okay? For compounds that are not conjugated at all, it'll be 200 or less. I don't think that's out of the overly mean of me to ask you to. I don't think that's unreasonable for you to remember that our baseline is 220 for UV-Vis. So I will not provide you with values for those. You should just remember that. if I ask you to predict a lambda max, if you wrote about 220 for just two double bonds conjugated, that would be correct. If you had multiple things conjugated, if you said something like, between 240 and 300 or something like that, that would be a range that would be acceptable to me. So, just really what I wrote in this paragraph here is what you need to know about lambda max values for UV-Vis. I don't think that's unreasonable. So that's it for this chapter. Study hard, practice up on this stuff. We'll see you for the next one.